Hi, this is Kevin. Welcome to my lecture on Chapter 5 of the Zelle 3rd edition Python programming text. And Chapter 5 is about strings, lists, and files. And the main title sequences, I think we're going to find out that whereas strings and lists are formal Python sequences, files are not. They are Python iterables. And they share a lot in common with Python sequences. And that's why these three things make a lot of sense in the same chapter. There are going to be two parts to this lecture. This is part one, and then there'll be a separate recording that's part two. Okay, I'm going to leave the objectives for you to read for yourself. And we begin by talking about the string data type, okay? And text is just a natural data type for computers because one of the common use cases that we have, at least for personal computers, is word processing. So we're pretty used to working on our computer and creating a whole bunch of text. So a string in Python is a sequence of characters enclosed in some kind of quotes. In the text, you're going to see that the author encloses his strings in what I call double quotes, whereas I am going to encourage you to take a more modern style and put them in apostrophes, which I'm going to call single quotes. Okay? So here's some code being typed in at the console or the REPL. So we created string 1 and we gave it the value hello. And let's see, we created string 2, we gave it the value spam. You can see that you alternately can use the double quotes or the single quotes. And then when we say print string 1 comma string 2, we get hello spam. And you'll notice here that we have a space in between. And when we print a list of things that's separated by commas, every place we have a comma separator, print is going to insert a space into the resulting printed output. If we call the function type on string 1, it says it's a string created with class string. And if we do the same for string 2, it says the same thing. Okay, so if we want to get a string value as input, we just have to call the input function. And as is typical, we're going to put as the argument or the parameter that we pass to the input function, whatever the prompting string is that we want to use. And note that it's a good practice, and I'm going to expect people in my class to add an extra space after the colon such that when the user is going to type in the value, it's not right up against the colon. It's a usability thing. So if we did this at the REPL and we entered John and we printed the string hello, a comma, and then the variable first name, it would say hello, John. Notice that the input is not evaluated. Well, it definitely is not going to be evaluated in my class because we don't use eval. After chapter 2, we gave up on eval. So what we really want to say here is you don't need to call a further function after you call the input function to prompt the user for the string because it's coming as a string. All input comes in and out from the user as a string. So because of that, we don't have to further convert it. Like if it were a number, we'd probably be calling int or float on it. We learned in chapter 3. Here we're saying in chapter 5, if we just want a string, well, that's what we get when we call input. Okay? No further conversion required. So strings have some interesting capabilities. One of them is called indexing. It allows us to refer to individual characters within the string using an index number. Okay, so the only thing that's odd, as in a lot of things with Python, is we begin to count with 0. So let's take a look at some examples. Okay, so here's the string hello Bob, kind of filleted out so you can see the parts. So here are the individual characters, and underneath we've added the index number. So this capital H is index 0, and the small b at the end is index 8. So here's some code at the REPL. We assign the string hello Bob to the variable greet, and then we type greet index 0. And you'll remember at the REPL, if we type a reference, if we type some kind of expression or variable name in the REPL, it's going to print the value. So the value of greet index 0 is this capital H, and that's what we got. And then we decided to print greet index 0, comma, greet index 2, comma, greet index 4. So we got a capital H, lower L, lower O. Notice, because we had the commas separating these expressions in the print, well, we got a space between each of the characters. Okay? And in the next example here, what we're trying to show you is that it doesn't just have to be a literal number in the square brackets. It can be an expression. So if we say that we want to print greet index x minus 2, where x is 8, okay, it's going to print greet 6, and greet 6 is a capital B, and we got a capital B. In a string of n character, the last character has the index n minus 1 because we start counting with 0. So the string hello Bob is 9 characters long. The first is index 0, and the last is index 8. And this all has to do with the 0 counting. Okay. We can also index from the right side using negative indexes. And this isn't something that people do all the time, but we will see an instance of it relatively soon. So a greet index -1, okay, is going to be the last of the characters. So it's -1 is the last character in the string. Greet -3 is -1, 2, 3. It's a capital B. Okay? And you might think that you won't get the use case for this, but again, we'll see one before the chapter's out. So indexing returns a string containing a single character from a larger string. So in Python, if we use an index expression and we get a single character, what's the type that we get back? Well, it's a string consisting of only that single character. In some other languages, like for instance in Java, there are different types for individual characters and single character strings. That's not true in Python. We can also access a contiguous sequence of characters called a substring through a process called slicing. So contiguous in a row, one after the other. Okay, so how does slicing work? Well, so I think this is saying that we're going to have a variable name and that we're going to have square brackets, just like we were indexing. But instead of having one expression, we're going to have two, and they're going to be separated by a colon. Okay, and the two values or expressions are start and end. Okay, start and end should both be ints. Okay, so they can be literal ints, or they can be some kind of expression that's going to resolve to an int value. The slice contains a substring beginning at the position start and runs up to but doesn't include the position end. So end is poorly named, and it turns out it's the first character that you don't want included. Okay, so again, we're going to go back to this picture of the contents of the variable greet, and it's got the value string hello Bob. So if we at the REPL, if we type in greet and then in the square brackets do 0:3, okay, well 0 is the first one we want and 3 is the first one we don't want. So we're going to get 0, 1, 2. We're going to get HEL, and we do. Greet 5, 9. 5 is the first one that we want. 9's the first one that we don't want. There isn't even a 9, but this is how we express it. Okay, and so we're going to get space BOB, and that's what we got. If we say greet nothing :5, this means begin at the beginning of the string. That's what the nothing means. It's a special meaning for no value there. Beginning at the beginning of the string, and then the first one that we don't want is 5. So we want HELLO. 5's the one we don't want, so we're going to get hello. If we code greet and then 5, nothing, well, we're going to start at 5 and we're going to go all the way to the end. So we're going to get space BOB, space BOB. And if we have a slice expression that just has a colon and doesn't have a begin value and an end value, then by default it starts at the beginning and it ends at the end. So we're going to get hello Bob. Okay, now I just want to point that even though this works, why you would code this, I'm not really sure, because you would get hello Bob if you simply use the variable name greet without this square brackets expression on the end. Okay, but that's how it would work if you decided that you were going to do it. Okay. So what if we want to put two strings together and create a longer string? Well, one really handy way to do that is to use an operator, the plus, called concatenation. And you might say to yourself, well, isn't the plus operator what we use for addition? And it is. So Python is one of the languages in which certain operators have more than one meaning depending upon the context. And in computer science, we call that overloading. So the plus operator is overloaded. It means different things depending upon the context. So if the two operands on either side of the plus are either if they're strings, either associated with a variable or just a literal string, well, that's going to mean concatenation. And then there's another thing that we can do is that we can use the asterisk operator, which when used with number types means multiply. When used with string types, it means repeat. And we'll look at some examples here. Okay, so if we wanted to create the express, if we wanted to create a string from spam and eggs, if we use the plus operator to concatenate them, then you can see here the result is spam eggs. Not very readable, but that's what we want. If we wanted to concatenate three strings, like spam and eggs, we would get spam and eggs. Okay, and if we were really doing this, we would have probably added some spaces at the beginning or the end of the words so that it was more readable. What if we want a string to repeat? Well, we just use an integer, an asterisk, and a string. So 3 asterisk spam takes on the value spam, spam, spam. And spam asterisk 5 takes on the value, and I won't say it, 5 spams. Okay, 3 asterisk spam plus eggs times 5 creates spam, 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 eggs times 5. Okay, if you want to know how long a string value is, you call the len function. Len is short for length. Don't ask me why they couldn't have typed out the whole word. So the len of spam is 4. Okay, and it turns out that strings, in addition to being one of the Python sequence types, are a Python iterable. What does it mean to be an iterable? Well, it means that you can iterate over the parts using the for in construct. So because of this, we can say for ch in spam, print ch, comma, end equals space. Okay, so what goes on here? Well, first of all, I would prefer that he typed out character, okay, but he didn't, okay. It's printing each individual character, or each individual ch, as I would say. And then this keyword parameter is telling us instead of a new line after each thing we print, which is the default value for end, we're going to print a space. So as a result, we got each individual letter separated by a space. each of the characters, including the special character asterisk. Okay, so what are the operators and the expressions for this string data type? Okay, and when we say the data type, this applies to variables that have an associated string value and string literals as well. Well, the plus operator can be used for concatenation. The asterisk can be used for repetition. If we have a single value in square brackets after the string, we are indexing it. We're going to get back one value. If we have potentially two values separated by a colon, we're creating a slicing expression. And if we want to get the length, we call the function len. And because strings are iterables, we can iterate over them with a for-in construct. So we can say for variable name in string name or literal string, and we iterate through the characters. Now, we're coming to the first of the programs, and if you've been following along with my lectures, you'll know that in the current recording of the lectures, I'm showing you the programs as the author wrote them, but then I'm showing you a refactored version because the author's style is kind of professorial and a little bit old-fashioned. Okay, so I'm going to bring over the first one, which I'm sorry, I've got the wrong one up here. The first one is called username. Let me find that. Username, and then username refactored. So let's bring over username, and here's the program. So this is the program as was distributed with the files that came with the book, okay? And his typical style for these is he has a comment up top with the name of the file, and then he has a comment that states the intention of the program, okay? And then he gets into the code. At this point, we're putting all of our code into main, okay? So he follows that. And then we have a call to main at the bottom. And one thing he doesn't have 2 lines after main, okay? And that's causing that PEP8 style error. So I corrected that. He also has comments that are coming from his pseudocode, okay, and you see them here. And I just want to emphasize for you that that's not how we do it in the workaday world, right? So let's go to username refactored, okay, and we're going to see that there's no comment with the name of the file because for those of us who are working in the field as compared to a book author, okay, if we want to know the name of the file that we're on, we just look at the tab at the top of the editor. So this one is called username refactored, okay. There are no simple comments at the beginning of the program because the kind of real Python way to document the intention of a program and some of the details is to have this triple quoted docstring at the beginning. So that's been changed, okay? And then the comments that really came from this pseudocode are kind of good for lecture material, okay? But that's not the way we're going to expect you to program, okay? The combination of knowing how to code and having used good variable names and later on good names for functions is going to allow us to write our programs without a whole lot of single line comments. Okay, so we took out all the comments because I didn't think that they were kind of workplace appropriate. So what's going on here now? Well, the first thing is we're printing a message that says that the program is running. That's something you can do. It's kind of polite. You don't absolutely have to. And then I've changed the variable names for first and last name. I forget what he had, but he had worse names. First and last. It's not that hard to say first name, last name. Okay? And then, of course, we're calling input. We don't have to further convert it. These are strings. Okay? And then we're going to form the username by using an index expression that's going to give us the first letter of the first name, and then a slice expression that's going to give us the first 6 letters of the last name, okay? Notice that this 7 is the first one we don't want. And because we don't have a first value, that means begin from the beginning. And of course, the plus is going to say concatenate them. And then we print your username is, and then we print the username. So if we run this, and I use my values, so please enter your first name, Kevin, last name, Trainer. Your username is ktrainer. Now, I'm just going to point out, and I'll be doing it throughout this lecture, that in the chapter that we're in right now, we're formatting strings using the concatenation operator. And that's a little old-fashioned. In the supplemental material that I have for chapter 5, I'm going to teach you an alternative approach to this called F strings, okay? But you're likely to find a whole lot of code that doesn't use F strings. It does formatting using concatenation. And so the examples I'm going to show you for the chapter are going to use the concatenation approach, and the F string will be introduced in the supplemental material. Okay, so I got us through that. Okay, now the next thing that he wants to show us is that you can take a string and cram a bunch of things into it, like the abbreviations of the months of the year. Here we've got Jan, Feb, Mar, all the way through Dis. And so these are the 3-letter abbreviations of the months of the year. And you could use those to convert a date that you get in numbers to a prettier date that included the 3-letter abbreviation for the month. Okay, and he's saying here about how would you slice out the 3 letters that you needed? Well, you would take the number of the month, okay, and you would do a slice expression with it. Okay, and that's going to lead us to another program, but we're not there yet. So here's how we would do this. I'm sorry. I don't know why that does that. So for January, you can see the number of the month is 1, but the position that we need for the slice is actually 0. Okay, so we want the 0th one. For April, okay, uh, it starts at 9. Okay, and so um, do we really want you to do this in the real world? Like, is this the way to print, to pretty print odd date? It's not, okay? It's going to turn out that there are at least two packages. There's the date package and the calendar package. Each of them has a way to turn a number date into a pretty text-oriented date, and those would be better approaches in your code that you would write in your day job. We just want to show you that you can pick things out of a string, okay? So we come to the second of the programs, which is called month, okay? And let me bring that over, okay? So here is the code that came from the book for month, okay? And again, I'm going to really work with the refactored version. And again, it's got a comment with the name. We're not going to want that. We're going to want a doc string here. We're not going to want the individual line comments because it's not what people do on the job. It's what instructors do on programs that go on to slides. Okay. And we also have the problem here that this variable name down on line 14, month abbreviation, is not a properly formed Python name. It would be a properly formed name in Java or JavaScript. And I'm thinking that somebody probably translated a program from Java or JavaScript and forgot to clean up the variable name. Okay. So let's go to the month refactored, and I just have to find it here. So month refactored is right here. Okay. And of course, you can see this is a much shorter program when you take out all of the comments and the noise, okay? It makes it easier to read. And what I'm saying is not that documenting programs is bad, okay? There are times when we want to add further documentation to programs. But what you're going to find as you become a more mature programmer is if you simply write clear code using easy to understand variable names and then later function names when we get to chapter 6, you're not going to need a lot of extra comments. Your code's going to tell the story. Okay. So the variable name that we're using for this string of the months abbreviation is months. Okay, we prompt the user for an integer. Okay, that's the number of the month that they want. Okay, that because it's an integer value, we need to convert it to an int after we get the string. Okay, pos is what he's calling the position. Do I like that? No. Let's refactor that. Let's rename that, and let's call that position. Okay, that looks better to me. Okay, so the position that we're going to start with to retrieve this is going to be n minus 1 times 3. Okay, so if we want January, that's going to be 1 minus 1 is 0 times 3 is 0. Yeah, that makes sense. Okay, because January is right in the beginning. It has no offset. What if we want February? So that's going to be 2 minus 1 is 1 times 3 is 3. And where do we start? 0, 1, 2, 3. Yeah, that's going to work too. I changed the name of the variable to month abbreviation because I can type that many letters, and I'm thinking that you can too. And here we're saying from months, we want to take the slice. I generally like to do this: position space colon space, and then we've got position plus 3. I'd put spaces in there. But it doesn't like my it doesn't like my extra space. So let's put that back. But position plus 3 is easy to read when we add the spaces. So I guess we're not going to add spaces around the colon. Okay. And then we print this. So if we run this, enter the month number, let's try January, 1, Jan. Okay. And let's do it again. Let's try November, 11, Nov. Yeah, that seems to be working. Okay. Let's try the other endpoint. Let's try 12. We always want to try the boundary values. Yeah, that's decent. That's working just fine. Okay. So that's the refactor version of month. So he admits that one of the weaknesses here is we're using this abbreviation. And this is, again, as an exercise to show how to pull things out of strings on the basis of, say, some formula. This is interesting, but as a way to look up a month name, it's kind of old-fashioned and wrong-headed. So it turns out that what we really probably want to do is we really probably want to use a list. Okay, so this is where we begin to segue from talking about strings as a sequence of characters and lists as a sequence of items or elements. Okay, so we're saying that the same operations that we were able to apply to strings, we can apply to lists. So this first expression is the list with 2 integer values, 1 and 2. The second one is a list with 3 and 4. And if we concatenate them, we get one list with the items 1, 2, 3, 4. We can also use a repetition factor. So if we take the list 1, 2, and we repeat it 3 times, well, we get a list with 1, 2, 1, 2, 1, 2. If we take a list that has the strings A, B, C, D, F, and we ask for grades index 0, well, we get A. If we ask for the slice grades 2 through 4, we get 0, 1, 2. Okay. 3, we get C and D, but we don't get 4 because 4, unfortunately, is the first one we don't want. And if we ask for the len, or length of grades, we get 5. There are 5. Okay, so those same operators that work so well with characters work on lists. Pretty cool, huh? Okay, so strings are always sequences of characters, so they can only have one kind of item type in them. But lists can be sequences of arbitrary values, okay, which means lists can hold items that are any of the Python types. So they could be strings, they could be ints, they could be floats. They could be lists. You can have a list of lists, so any kind. And then the other thing is that they don't all have to be the same type. Now, if we're collecting up a bunch of things, they're usually the same type, okay? But sometimes when what we're collecting up is, say, all of the items that are user typed into an input form, the things might look rather different. Okay, well, if we're getting from an input form, I guess they'd all be strings, but they could be. So you can have a list that includes here an int, a string, an int, a string. Perfectly good, okay? Although, I have to point out, usually we have a list of fairly homogeneous things, okay? Lists as sequences. Okay, so lists are sequences, so we could take our month abbreviations and put them right in here. Okay, so and then we could use the same kind of math, okay, to figure out which index we wanted to bring back. And we would bring back the entire abbreviation. Okay, so he shows us a program that he calls month 2. He, by that I mean the author, John Zelle. Okay, so let me find month 2. Month 2 looks like this. Okay. And I've refactored this to kind of jump ahead. In a slide or two, the author says, hey, you know what? As long as we're putting strings in here, they all don't have to be the same length. Okay? We'll just put the real names of the real months in here. Now, you might want the 3-letter abbreviations. Okay? All right. So what happens when I refactor this? Well, that brings me to my month 2 refactored. And again, I've cleaned up the doc string. Okay, and I've used the full names of the months in English. Okay, we have these square brackets create a list initializer. This is how you give initial values to lists. Okay. We prompt the same way for the number of the month that we want. We're putting the value into the variable or associating it with the variable name n. Not a great variable name, but I decided to keep it. And then we print the month name is, comma, next item, months n-1, okay, because again, they're numbered 0 through 11, so we need to convert that. And then we are adding on a period. And again, I just want to point out here that once we get to the supplementary material for Chapter 5 that I'm going to be adding for Chapter 5, we would probably print this line with an F string, okay? But right now, we're just going to use a normal print to do this because this is the way that people did the F string, which again, I'm going to introduce in the supplemental material, didn't come along to Python 3.7 when the author wrote this book. He wrote it with Python 3.4. So when he wrote the books, there were no F strings. And you'll find a lot of code from other people or in books or in libraries that was written before Python 3.7 and takes this approach to formatting output. So we just can take this and run it. Okay, and again, we'll take number 1, and that's January. And let's take number 12, and that's December. So we tested the boundary values. So that's pretty good. Okay, so he's kind of talking us through that code, and I've already talked you through the code. Now, one thing about lists that, lists are sequences, and strings are sequences as well, but lists are mutable and strings are not. Okay, so we can't change the characters that are in a string. I know we write expressions all the time that look like they do, but those expressions throw off new string objects. Okay, whereas lists are really the first of the data types that we're going to learn about that are truly mutable. Okay, so the list object has items in it, and we can add items, we can delete items, we can sort the items, we could change the value at a particular part in the sequence. Okay, so this mutability is something that lists have that character strings do not. So here we are illustrating that we have a list. We try to change my list 2, which is of course the third one. No, we query what's in my list 2, which is the third one, 15. Then we set it to 0, and then we type my list, so it's going to print the value, and then now you can see the third value is 0. But if we try to do that with the string, that's not going to work. So if we set the variable myString equal to hello world, and then we query myString index 2, we get a lowercase l. But if we try to set that to a lowercase p, kaboom. Why is that? Well, because this object does not support item assignment. Okay, it just doesn't. String representation. Inside the computer, strings are represented in a binary format, ones and zeros, just like the numbers are, ints and floats. A string is stored as a sequence of binary numbers, one number per character. It doesn't matter what value is assigned as long as it's done consistently. So we're saying this in kind of great computer science thinker mode. Okay, if we're trying to encode Python strings, there is a scheme for that called the Unicode encoding scheme, and that's what's used in Python. But the mothers and fathers of Python could have picked another encoding scheme like ASCII. That's an more old-fashioned one. As long as there's a scheme and everybody subscribes to it, it works just fine. So in the early days, we used a system called ASCII, ASCII, and it had 127 bit codes. So the ASCII encoding scheme only allowed us to encode 127 different character glyphs. Okay. Now Python has adopted the Unicoding encoding scheme, which will allow you to encode more than 100,000 character glyphs. So The ASCII system is kind of old-fashioned and maybe too ethnocentric to maybe North America and Western Europe. And the Unicode system is much richer, includes characters for languages that are used all over the world, and is the more modern approach. So, how does this encoding scheme work? Well, one of the things that you can do is you can use a function called ord and give it a character like uppercase A, and you'll get back the decimal encoding equivalent of an uppercase A. So ord of an uppercase A is 65, ord of a lowercase a is 97, and the opposite function is I say char because it's turning it into a character. So char of the integer 97 is the lowercase a again, and char of the integer 65 is uppercase a. Okay, so on the basis of that, it's possible for us to write a demonstration program in which we can take a message that has been encoded into these Unicode numbers. They're actually called code points, each of them. And then we can decode them and turn them into characters. And it's possible for us to do the opposite one, where we prompt the user for a message and plain old text, and then we can turn around and we can encode them into these Unicode numbers or code points. And that's what we're going to show you in just a few seconds. Okay, so what we can do is that we can create an encoder here, and we have a program that's going to show an encoder. Okay, so let's look at that. So this is the file version. So the author's version is called text to numbers. Okay. And you'll see that it's got the usual, treatment that programs get in the book. And so the refactor version, text to numbers refactored, is kind of my cleaned up version. Okay, so I begin with a doc string, and typically with a doc string, at least according to a very popular convention for coding them, if you've got more than one line to say, okay, the first line should be a summary. Okay, so that's where I took his summary comment. And then the second line should be blank. And then the detailed information that somehow expands upon that summary comment begin on line 3. So what I've done too is to say, when we test this, what data should we try to test it with? And the data that I want is for the message to be the string, my secret message. Okay. So we print some kind of introductory messages. Again, we don't always do this, but it's a nice way for the user to know that a program is running. and which one is. And then we prompt for the message. Please enter the message to encode. Okay. And then we print the message. Here are the Unicode codes. Okay. And then for character in message, I think he had a worse variable name. We're going to print the ord of the character. That's going to give us the decimal encoding of the character according to the Unicode standard. And we're going to use this keyword parameter end equals space to make sure that we don't put each of the numbers on its own line, but we put them on one line separated by spaces. Okay, so this cleaned up refactored version. Let's just copy my suggested test data, which I added. Okay, and I'm going to run this. So please enter the message, and I'm just going to paste it, my secret message. Okay, and here are the numbers. Now, we call these in Unicode parlance, we call each of the numbers a code point. A code point stands for the character or glyph that is going to print when you print that character. Okay? Okay, so they're numbers, but they're a special kind of number. These are the Unicode code points for those glyphs or characters expressed as decimal values. You sometimes can see them represented in hexadecimal. Hexadecimal is base 16. The good thing about hexadecimal is there are fewer digits. The bad thing is that they're less friendly to read. So when we call ord, we get the decimal. Okay, so that's how this works, and not too surprising, huh? All right, so let's get back, make a point or two from the slides. Each time through the loop, a number from the input is converted to the so this is the beginning of a decoder. Okay, so the outline for the decoder, that's kind of pseudocode. Get the sequence of numbers, I call them code points to decode. Create an accumulator variable for text. Now, we've done accumulators for multiplication. We've done them, you do them more typically for addition and subtraction, but you can accumulate strings of text. And if you're going to have an accumulator like this, well, you assign the empty string when you initialize the variable. For each number or code point in the input, convert the number or code point to the appropriate character. Add the character to the end of the message. We're going to do that with concatenation, and print the message. Okay. The variable message is an accumulator. Initially, he's sent to the empty string. Each time through the loop, a number from the input is converted to the appropriate character and appended to the end of the accumulator using concatenation. How do we get the sequence of numbers to decode? Read the input as a single string, then split it apart into substrings, each of which represents one number. Okay, and there it turns out that there's a method called split that's going to do that for us. So here's the new algorithm and something that's more pseudocodey. Okay, now here's the slide that tells us how to use split. So if we take a string and call split on it, and it has intervening spaces, well, the default is it splits on the spaces. And what do we get back from a call to split? Well, we get back a list of strings, okay? And they don't include the separator. So when we split, there's always a separator, and the separators get eaten. And by default, that's the space. So we get hello, string, methods, exclamation. Okay, that's how that would work. Split can also be used on, when we call split, if we don't want to take the default separator, which is the space, if we wanted to use a comma, if we had these values separated by commas and we called the split method, then we would get back a list of the string values. Notice that these are still strings. Okay, so let's take a look at the decoder, okay? And that one is called numbers to text. Okay, so here's numbers to text. All right, it looks like this, and it's got all the improvement opportunities that we've been seeing all along. Too many comments, badly formed variable name. Too many comments up here, should be a simpler doc string. Okay, so we're going to open up numbers to text refactored. Okay, and I've cleaned it up a lot. First of all, I've got a doc string, and I've added this suggested test data, and this is coordinated with my other improvement of the encoding program. This is the decoding program, and this is the number or code point equivalent of my secret message. Okay, so we print an introductory message. We prompt for the message. Okay. Oh, okay. So I call this the encoded message. Okay. If you look back at his program, he's just calling it the message, and it gets hard from the variables to figure out what's encoded, what's not. Okay, I've improved the variable names such that the encoded one, which is this list of digits and spaces, is called encoded message, and then the decoded one, which is called message. I thought about calling it a decoded message, but I thought it was maybe a little too long-winded. Okay. And then I say for Unicode code point as string. So these are not Unicode numbers, they're Unicode code points. That's what the Unicode people call them. Okay. And when we get them in, when we prompt the user, they're string values. Okay. And for each of them in, we take the encoded message and we split it. So the split returns a list. We don't save the list explicitly, okay? We have it, we just use it in this for in construct, okay? So what do we do the first one? Well, we convert it to an int. So when we convert Unicode code point as string, it becomes Unicode code point as int. Now, some people would think this is a little long-winded, but I don't. And that here's what we do. Here's where we're accumulating using a concatenation. So in the beginning, the message is empty. But every time we go around and process a code point, we add that onto the end. And then when we're done and we print it, we have the message. So let's give this a run. Okay, and what are we going to give it? Well, I'm going to give it the opposite of, I'm going to give it what we encoded with the last one. Okay, so if you give it that, we get back my secret message. Okay, now, is this the optimal way to do this? It turns out it's not, okay? Accumulating a text by a concatenation like this is pretty expensive, because every time we do this concatenation, we have to create a new string object. This looks like it's just adding on to the object, but the fact is it creates a whole new object every time. So there's another approach to accumulating the string that's more efficient. And this is what he introduces in numbers to text 2. Okay. And again, numbers to text 2 has all the kind of opportunities for improving that I have improved upon when I did numbers to text 2 refactored. Well, where is it? It's numbers to text 2 refactored. There it is. Okay, so how's this one different from the last one? It's only different in the respect to how it's accumulating the characters. Okay, here's what we're going to do. Characters can be the elements or the items of a list. So we're going to have characters be a list, okay? And then every time we create a character by calling char on code point as int, okay, we're just going to append that character to the list. That's going to create a string with that single character. Okay, so instead of using concatenation, what we have now is we have a list, and each of the items in the list is one of the characters that we want. And it turns out for this kind of application, the interesting thing to do is to use the join method of the string class. And this is a little bit hard to explain. It says here, I am a string. In this case, I'm the empty string. Oh, probably we want this to be 2 apostrophes. Yeah, okay, yeah. So I am the empty string, right? And I want you, so here's what join does. It takes all of the items in the list characters, okay, and it joins them together, okay, using the string as the separator. Okay, how does that work? Okay, well, if we have the empty string, then there's no separator. So it just joins them right together. Okay, so let's see how this would run. Let's give this a run now. Okay, and again, I'm going to give it that my secret message encoded in the Unicode decimal code points. I'm going to put that in there. And there it is, my secret message. Now, what if I wanted to use something else to join them. Like, what if I wanted to use a hyphen? Okay, well then it would put a hyphen in between each of them. Let's see that run. And I need to get this over here. So if we run this again, okay, and I think I can paste this in again. Yeah, there we go. There it is. Okay, you can see how it put the hyphen in everywhere it would have put nothing in from the empty string. So we want ours to be the empty string. It's a special trick for joining a bunch of text together. Okay. And so we'll run this again. And we'll give it our code points again. And now it says my secret message. So this accumulating text in a list as a series of strings, even one character strings, and then joining them with the join method of the string class is a more efficient and more sophisticated approach to accumulating text. Okay? There you go. All right, so we're getting pretty close to the end for this. Okay, the end of part one, that's what I was saying. So there are a lot of string methods, and you're going to become more familiar with them over time. Okay? Now, I want to point out again that you might think of, if we have a string in variable s and we call the method capitalize, and you might think that it's going to change the value that's in the string that is pointed to by s. But no, it does create a transform value, but it's a new string. It's a copy of s with only the first character capitalized. Okay. If we call title, well, then the first character of each word is capitalized. That's title case. If we call center and we give it an integer or an expression for width, it will center center the text with surrounding spaces to the width that we specify. If we say we want to count and we give it a substring, it's going to count the number of occurrences of the substring in S. If we call find and we give it a substring, it'll count the first position where the substring occurs. That'll be the index of it. If we tell it to join, well, we're going to get the join. Okay, the value of the string is going to be used as the separator. If we use ljust and a width, it's going to work like center, but it's going to be left justified. If we say lower, it's going to shift it to lowercase. If we use lstrip, it's going to remove leading white space. Okay. If we use rstrip, it's going to remove trailing white space. If we provide a character in here as a parameter, like asterisk, if we have leading or trailing asterisk, we can strip them away. If we want to replace, we can replace old substrings with new substrings. Again, we're getting a new string. Find a substring. it's like flying, but it returns the rightmost position. R just is going to justify, it's going to right justify and pad on the left. Our strip, I mentioned already, is going to take away the trailing white space. Split is going to split into a list of substrings. The default is it's going to do it on the space. If you pass a parameter, a string as a parameter, it will use that as the separator. If you call upper, it will shift all the characters to uppercase. Lists have method 2, methods 2. So we know about append because we used that back in the last of the programs. Append adds another item onto the end of the list. So I think this is so we can avoid this recopying using lists of characters where each new character is appended to the end of the existing list. Oh, yeah, he's working up to numbers to text 2. So that was numbers to text 2. We've already talked about that one. Okay, and as you can see, we're using append. Okay, so now he goes on to talk about encryption. Okay, and this I think is a good computer science topic. It's interesting to information scientists as well. The fact is, we can already see that it's possible to encode plain text into numbers, okay, using Unicode code points, okay. If we were to encode it to something less predictable and hard to unencode without knowing the details of the scheme, well, that would not only be encoding, it would be encryption. And then if we were to use details of the encoding scheme to decode it, well, that would be decryption. And he goes on to talk in the chapter and a couple of slides here about modern approaches to encryption and decryption. And that's not really what this course is about, so I don't think I'm going to say anything further about that. Okay? Very interesting stuff, but I don't want to do a cursory job of it. And that brings us to the beginning slide of part 2, so I'm going to pause here and say bye, and come back and see us in part 2. Bye-bye.